Hello, my name is Dr. Nira Chamberlain, and thank you for having me here at the Royal Institution. And the topic of my talk today is, what's the point? Why maths really matters. Now, all around the world, people, school children, saying that, and even parents saying, what's the point of maths? When will we ever use it? It's boring. I do not like mathematics. Now, one time, it was about 7 years ago, I started doing some school outreach through a charity, and I go into schools and talk about mathematics. And then at the end, somebody put their hand up there and they said, "Sir, but what's the point of mathematics?" And I said, "Why? What's the problem? Didn't you hear my talk?" And said, "Yeah, but what is the point of mathematics? You haven't dealt with the elephant in the room. What is the point of mathematics?" So I decided just to turn it around, and I said, "Well, why don't you like mathematics?" Well, and he says, "Well, I hate mathematics. Why? Because I think it is useless." I'm thinking, "You think it's useless?" I said, "Yes, I think it's useless, and my parents think it's useless, and I think it's too difficult. Surely there must be somebody, the only people that can actually excel in mathematics must be those who have a mathematical gene. You know, only those who have, let's say, a mathematical gene can excel in mathematics. So what's the point of mathematics being compulsory for me?" And I heard this person, and I decided from then on in is always to actually deal with this elephant in the room. Now, the most of my talk will be talking about why people, showing that mathematics is not useless. But let me talk about this aspect that is there a mathematical gene, and saying that mathematics is difficult. Well, the person on the right, the gentleman on the right, his name is Cedric Vernali. Now, Cedric Vernali is one of the greatest mathematicians in the world today. And he won the most highest award in mathematics called the Field Medal. Now, he wrote a book. And what I'm going to do is I'm going to paraphrase some words that he had in his book. And he said this, that a mathematician is never, ever quits. That's a mathematician. I'll say that last phrase again. A mathematician are those who sees a problem and never, ever quits. So us mathematicians who enjoy mathematics, we still find it difficult, but the thing is, we go for it and we never, ever quit. And so, in terms of, what is the point of mathematics? I mean, if you ask 100 different mathematicians, they will probably give you 100 different answers, all of them relevant, but it's all based on their own personal experience or their own personal education. So let's say if they're a pure mathematician, then they answer one way. If you ask, let's say, a teacher, they may talk about numeracy, may talk about finances, may talk about organization using mathematics. But I want to come from a different perspective, from my own perspective, and that's the perspective of a field which is called mathematical modeling. Now, mathematical modeling is the use of mathematics to solve novel real-world problems. So in terms of mathematical modeling, when I'm dealing with a problem there, I will not find the answer in the back of the book. The answer that I'll find for my mathematical models is more determined by how close to reality the mathematics is trying to describe. So, as I said, my name is Nira Chamberlain, and this is my story. Now, these two here, these are my parents, and my parents came from Jamaica in the 1960s, and they were part of what was called the Windrush generation. And so they came from different parts of the island of Jamaica. They didn't know each other in Jamaica. They met each other in England. They got married. They started a family, and during when I was growing up in Birmingham, when I was in my teenager, my parents used to say this to me. They used to say, "You don't need anybody's permission to be a great mathematician." Now, with me, I only half believe what my parents said back then, but this motto stuck with me for the rest of my life. This saying, "You don't need anybody's permission to be a great mathematician." And this is my parents. And it's about 7 years ago at my PhD graduation. And that's my dad, and that's my mum. And I can really just trace that route of me getting a PhD in mathematics. This saying, "You don't need anybody's permission to be a great mathematician." So I went on, and in my career, you know, as was said in the introduction, I've been doing a lot of mathematics all around Europe, and some people have decided to depict me as some sort of cartoon scientific superhero. Now, am I a scientific superhero? I wouldn't say so, but that's what some people have drawn me at. But what was good was that this year I actually became the president of the Professional Learned Society, the Institute of Mathematics and its Application. And I'm halfway through that term now. I've got one more year to go. Now, but one of my first tasks as president was I had to do a talk at Parliament. And what they said to me, they said, Nira, the national statistician has dropped out of this parliamentary event. So what we need you to do is that we need you to go to Parliament, stand up in front of all these politicians, stand up in front of the ambassador of Vietnam, stand up in front of all of these presidents of the other scientific societies and these postdoctorate and PhD students. And what we want you to do is we want you to sell mathematics in 2 minutes. I said, you want me to sell mathematics in 2 minutes? I said, yes, you've got to sell mathematics in 2 minutes. What is the point of mathematics in 2 minutes? So this is what I said. Ladies and gentlemen, mathematics is indisputably the greatest subject in the world. Why? It is one of the few disciplines that can teach science to scientists, engineering to engineers, technology to technologists, and I can go on and on and on. Mathematics is everywhere, and it is the lifeblood of any modern economy. Furthermore, a mathematical professor and a CEO of a tech startup once told me that mathematics is at least 100 years ahead of most disciplines. Is this true? Well, in 1796, the French mathematician Laplace described mathematically the idea of a massive star which no light could escape from it. Today, we now know this as a black hole. In 1939, the physicist Albert Einstein published in an article, the Journals and Annals of Mathematics, in which he intended to prove that such black holes were impossible. So, in conclusion, Albert Einstein was wrong, and the 18th century mathematician proved to be right. Mathematicians in the room, and you out there in the internet world, in today's modern data-driven economy, we are entering the era of mathematics. Who among you will be the next Hannah Fry, the next Andrew Wiles, the next Katherine Johnson, or Ramanujan? Even more importantly, make today be your first step, not your last. Finally, always let the world know that you are proud to be a mathematician. I told that, and the audience had the mouth open, and what I did, show the mic time, drop the mic. So, moving on. So, the question is, why maths matters? Part one. Now, I might have disagreed what Albert Einstein said about a black hole, but I do agree with this statement. He said that mathematics is the poetry of university maths graduate. He just graduated. He just finished his degree in mathematics, and he was quite bored. And so what he did, he looked in this book, and in this book, he had like the movements of the planet Uranus. And he could actually see that the Uranus had, his orbit was quite strange. And then from this, by using some mathematical modeling, he actually predicted that there must be another planet out there further beyond Uranus. And what he actually done, he actually used the poetry of logical ideas to predict the existence and the position of the planet Neptune. A number of years later, people with telescopes, scientists with telescopes, actually looked and found very close to where he predicted the planet Neptune, the poetry of logical ideas. So the question is, what has been my mathematical invention? So when people say to me, Nira, mathematics is boring, I say, well, mathematics is the poetry of logical ideas. And really and truly, my experience has taught me that mathematics is all but boring, because I've been working on problems such as stopping oil pipelines from exploding, or stopping airplanes from falling out the sky all around the world, or looking at volcanic eruptions and trying to come up with a mathematical model to come up with some evacuation plan when the volcano is exploding. one thing that was very interesting was one day I got approached by a Royal Navy captain, and he said this to me. He goes, Nira, I said, hello. It's expensive to build, but it's actually unaffordable to run. And do you think you can come up with some mathematical modeling way to solve this problem? And I said, let me think about it. And I said, have you ever heard the story Goldilocks and the Three Bears? And he says, I beg your pardon. I said, yes, Goldilocks and the Three Bears. You see, there's a part of the story that goes like this. See, Goldilocks, she goes into the house and she looks at this porridge and she eats this porridge, and this porridge is too hot. She eats the next porridge. That porridge is too cold, and then she eats this porridge, and that porridge is just right. And I say, there you go. That is how you solve your problem. And he just looked at me and he walked away, and I didn't see him again for another 2 weeks. Then he came back to me and he said, Nira, I said, can you follow me? And I said, so I followed him and I went into a meeting that looked like this. And I said, I went into this meeting. I said, hello. And I said, hello. And I said, what is this meeting about? And I said, well, this meeting's about us talking about cancelling this future project. But we have heard that you've come up with a possible solution. I said, oh, yes, I have. And I said, would you like to tell us about your solution? And I said, okay, have you heard the story Goldilocks and the Three Bears? And they said, I beg your pardon. I said, here we go. Goldilocks and the Three Bears. You see, Goldilocks, she goes into the house and she sees this porridge and she eats this porridge and she says, this one's too hot. She eats the next one and says, that one's too cold. And then she eats this one and says, that's just right. I see, there you go. That's how you solve your problem. And then they said this to me. Do you realize that this project is of national importance and you're coming up with some sort of nursery rhyme? And I said, oh, okay. Wait. Let me be a bit more specific, because what I'm telling you is the poetry and logical ideas. So what you need to do is that you need to get that ship, look at its capability, connect it to its cost, connect it to its design, and what that will create is that will create a whole series of nonlinear mathematical equations. Then you put those equations into a computer and you write an algorithm. You tell the algorithm, design me a ship that's not too hot, not too cold, just right. And then what you'll have is that you will have a ship that is affordable. And I showed them an example, and I says, oh, actually, we think that one could work. See, now, that was over 10 years ago. See, the question is, would you like to see what that ship looks like today? What you just saw there was the HMS Queen Elizabeth, which is the largest aircraft carrier that the Royal Navy will ever have. Now, somewhere on that ship, excellent, thank you very much indeed, somewhere on that ship, you will find a placard, and it will say Dr. Nira Chamberlain, and it will remain there for the next 50 years. So there you go. That is the use of mathematics in action, the poetry of logical ideas. Cool. Now, because of my mathematical adventures, you know, I was named by the Science Council as being one of the UK's top 100 scientists. They cited me for recognizing me for developing mathematical modeling applications for industry. So, National Award to show why mathematics matters. Okay, so now one of the things I could say is that most of my models I'd say about 67% of my models use something called the random walk. Now, the random walk is a simple but powerful mathematical modeling technique, and it involves, you know, logical statements and probability. So what I'm going to do is give you a little demonstration of the random walk. Now, let's say, for instance, let's say you start off with the variable x equals 50. Now, if you have, let's say, a calculator and you press its random, let's say you press its random number generator button. Now, if this random number is less than 0.5, add 1 to x, else minus 1 from x. Now, go back to step 2 and repeat this 9 more times. Press the random button, see whether it's less than 0.5. If so, minus 1 from x. If it's greater than 0.5, add 1 to x, and then do that 9 times, so you do it, and then write down the new value of x. See, now if you do that, see, the question is this: is it possible for that value of x to be an odd number? And also, in terms of mode, which is let's say the most free, because if we keep on repeating this over and over again, this trial over and again, you'll get different numbers. But what is the number that we're most likely to get, or the highest frequency number? Let's call it the mode. Where do you expect to see the mode? Would you expect to see it less than 50, equal to 50, or more than 50? Right? So you will see an actual poll where you can actually submit your answers to a poll, or submit what your thoughts are in the chat. So, but what I'm going to do is I'm now going to show you what the results are. And for that sequence, you can actually see that really and truly that the mode would be on the 50. Would we, because of the logic, every step that we find that we'll reach will always be an even number, and so you're looking at this symmetrical shape where we're saying 25, just less than 25% of the time would we end up, the new x value would end up, the final x value will be actually 50. So now if we actually repeated that again, so let x equals 50, press a random number generator button. And what this time, instead of saying less than 0.5, we say less than 0.7. Go back to step 2 and repeat this again 10 times and write down the value of x. The question again is, is it possible for that value of x to be an odd number? And again, where would you expect to see that mode? Would it be less than 50, equal to 50, or more than 50? And what I'm going to do is I'm just going to show you the result. Again, using that same logic, you will always, because you're taking 10 steps, you will always finish on an even number. And here you can actually see that the mode is over 54. Yeah, so it's more than 50. But the basis for this idea is you even doing things randomly and following these rules, there are some places where it is impossible to finish. It is impossible to finish on with x equals 51 or x equals 49. Also, it is impossible for x to reach 100, yes? But there are places where x is more than likely to finish, yeah? And that's the interesting thing about the random walk. So what I'm going to do is show you a demonstration of the variation of the random walk. And with that, I need the help of a pirate from the Caribbean. So the question here is this: hidden treasure. 10 years ago, Jack Sparrow hid 5 gold coins on a large desert island. However, he has forgotten where he had buried it. All he can remember is where he started from, and that he buried the first coin after 20 hours of walking, the rest after 40, 60, 80, and 100 hours of walking, respectively. So the question is, where are the gold coins buried? Now, if you look at that and you're thinking, well, really and truly, if let's say you're walking off in a straight line, and if you're walking at a certain average speed, surely the gold coins will be somewhere on the circumference of the circle, you know, not a problem, and relatively easy. However, speaking to Jack, he's added this complication. He says this: I might have changed direction after walking for an hour. I say again, I might have changed directions after walking for an hour. And he says this, he said, after an hour, I got really tired, so I sat down and I fell asleep, and then I woke up to continue my walking, but I forgot which direction I was going. And so I looked at my compass and I choose one of these directions, either north, northwest, west, southwest, south, southeast, east, northeast. He's gone off in one of those directions. So the question is, really and truly, where are the gold coins? Now, using the random walk, we can put that rule, that logical rule of him walking for an hour and then possibly changing directions, and continue doing that for 20 hours, 40 hours, 60 hours, 80 hours, 100 hours. And what we do a Monte Carlo simulation where we run this sequence a million times to create a probability field to find out where is the most likely places, probabilistically wise, where those coins are located. So here we go. Now this is after 20 hours of walking. Now the darker shades of green, it means the higher the probability of where the first coin is actually located. So this is 20 hours walking, and the red zone means a very low probability of those coins being located there. So this is after 20 hours of walking. 40 hours of walking, 60 hours of walking, 80 hours of walking, 100 hours of walking. So if we actually take a slice through that region, what we can see is that really and truly that there's a reasonable or high probability that those 5 coins are actually located very close to the origin where Jack Sparrow actually started walking. But even more so, what we're saying is the good news for Captain Jack Sparrow is by using the random walk, his search area has actually been reduced by 84%. Now, that is a very much fun example of the random walk, but there is actually a serious application. On the 8th of March 2014, there was a plane called the MH370, a Malaysian plane that left the capital of Malaysia, Kuala Lumpur, and was heading to Beijing. After a while, after a number of minutes, it disappeared off the air traffic control radar screen. And from this day to now, people have been searching for this airplane. Now, during the first year, it was assumed that the plane had suffered some engineering malfunction and it became a ghost plane and had landed somewhere in the Indian Ocean. However, when they sent all the military assets and rescue vehicles there, they found nothing. Now, evidence shows later on that possibly this wasn't to do with engineering fault or failure. This was possibly to do with a human factors, maybe to do with the pilot itself. And the question is, if this was to do with the pilot wanted actually to hide the plane, what could we do? Now, one of the things I have been doing in the past is I have been working with the Royal Astronautical Society, and I said to those pilots this question: if you wish to hide a plane, what rules would you follow? Now, by actually cataloging those rules and putting it through a random walk, what is hope is that we would actually create a new probability field to find out where that plane has actually gone. And that is a serious application of the random walk. This is one of the reasons why maths matters. Here we go. Why maths matters, part 2. It's because it is a beautiful and powerful subject. But mathematics is also good at solving real-world problems. So now, in the about 15 years ago, there was an MTV program, and I've changed the title a bit, but what I'm going to call it, it's called Big Up My Ride. Yeah, Big Up My Ride. And what they would do in this program is that they would take a very old, banged-up car, and they would actually transform this car into a new flashy car that's got all these mod cons and got all this technical stuff in it. Yeah, and this is what they would do. Now, in some ways, this is something that another skill that mathematical models do. Not only do we do the poetry of logical ideas, we also, what we do is that we actually do a transformation of old classical mathematical theorems into new mathematical models. So sometimes we take a classical mathematical theorem and apply it to a new problem, especially if it's the classical theorem is not fit for purpose. Yeah. So if I was, for instance, wanted to do let's say my own TV show where there's a problem and I take old classical mathematical theorems and produce this new mathematical model to solve these new novel mathematical problems, I would call it something like Big Up My Maths. Yeah, Big Up My Maths. So what is the first episode of Big Up My Maths? Episode 1, Mathematics versus COVID-19. Now, back in March of this year, something amazing that I saw was I knew that, let's say, COVID was very, very serious, because on the BBC News in the evening time, this was the first time I actually saw a nonlinear differential equation being spoken about and presented on the BBC News. Now, this is a version of what's called the SIRS model, the Suspect Infectious Recovery Model. Now, this is in the form of a differential equation. We can actually represent this in the form of a variation of the random walk called the Markov chain, where we have those who are a group of people who are in suspect, those that moved into infectious, those who really recovered or go infectious or actually died. Yeah. Now, what we have is that there's a probability of moving from one state to the other, or moving from one state and actually remaining in that state. But the problem was is that with this model, when we're actually applying, looking at COVID was a completely different type of virus. Even though this was used to look at how we look at how virus spreads, in terms of COVID was a completely different kettle of fish. COVID model looked more like this, where we had to look at so many different states and looking at so many different probabilities of moving from the different states, but also we had to look at the policies that would be implemented by the government to try and slow down the rate of infection. Yeah, so what we do is we had to big up the maths. We have to move from the classical mathematical theorem to a more comprehensive mathematical model to deal with the spread of this COVID. So now, one question was doing. Now, this was what we call is the Markov chain simulation. Now, one of the things that was actually occurring was back in March was the government of various countries were making a number of assumptions about COVID and was coming up with their own different strategies. Like there was one government that was saying, well, all we need to do is just implement, let's say, a herd immunity strategy, i.e., just let the viruses go spread right through the population, don't do anything, and people will become naturally immune. And don't worry, another assumption was, don't worry, you only can catch COVID once. And see, the question that was posed was saying, well, what happens if we do implement this strategy, and what actually happens if they are wrong? So in this graph, we actually did, let's say, a simulation of a North American city, which just is subject just to herd immunity. And what we're going to do is that we're just going to call that our baseline. And what we're doing here is that we're assuming that you cannot, you only can catch COVID just once. But let's say we put in that there's a probability of you catching COVID again and again and again. And then what you do is from that simulation, implementing those new rules, is that we move to this graph where we can see that actually the death rates actually increase to over 107%. And then the question is, okay, well, what happens if we implement some like, a little bit of, let's say, social distancing? What would that do? Well, this would actually move to this graph here, where the number of deaths from this herd immunity still increases to the death increases to 63%, because we still are taking into consideration that you could actually get COVID a multiple time. And then what we did is then we implement, let's say, a New Zealand solution where we go through, let's say, after a certain time, we go for total lockdown. And by doing that, we see that from the herd immunity that we can actually see that the number of deaths has decreased by let's say, 84%. But this was all quite interesting, but there was quite a debate about social distancing and should we do social distancing. So the video next shows you an experimental mathematical model of social distancing.
Okay, today we're going to demonstrate a mathematical modeling experiment of social distancing. What we have here are two rows of dominoes. This one is not doing social distancing, this one is doing social distancing. Look what happens when the first domino has coronavirus. Everybody gets coronavirus. Look what happens when this domino gets coronavirus. Social distancing works.
So that is, and let's say, as we all know, the fight on COVID continues. So episode 2, mathematics versus AI. Now, the late and great Professor Stephen Hawking did an interview with the BBC, and what he said was this: he said, the development of full artificial intelligence could spell the end of the human race. And so what he was talking about is the possibility of artificial intelligence takeover and the artificial apocalypse. So now, there was an article written in a magazine called Interesting Engineering by Jessica Milley, and what she put down, it was 11 times that AI beats humans at games, art and law, and everything in between. So, but what was actually interesting is it was this part here where it comes to about the AIs and the games of strategy, where she pointed out that AI can be more performant at strategy games too. So, the question that was posed to me was that how can we let's say, compete against a competitor that may use AI to develop business strategies. Because over in Europe and certainly in North America, what they do is they use computer simulation and operational research tools to model their competitor and come up with business strategies. And the concern was, what happens if we actually use AI to come up and find the most optimum solution and an advanced AI that comes up with a business strategy that would beat all its competitors? So, and the question is this, but if, for instance, a competitor could actually do that, would it could that competitor become a monopoly in that industry? And if it actually went into different industrial sectors, could that AI end up actually running the world economy, making decisions? The people will hand over decision making over to that AI for it to make decisions. But the question is this: now, if that was the case, would the AI make decisions conducive to social cohesion? Now, in the summer, there was talk about a program or a spreadsheet that was used, an algorithm that was used to determine the grades of A-level students, and this caused a lot of protest because some students that were predicted to get A star were getting much lower, and they're saying, well, how can an algorithm be used to choose what grades I get? So that caused a large-scale protest. Now, the question is, now that is just the tip of the iceberg. Let's say, for instance, we used a much more advanced AI system, a much more advanced algorithm to make decisions right across the board. Now, would the AI make decisions conducive to social cohesion? Yeah. And so the challenge for me, which was posed to me, it was saying, Nira, in terms of the business environment, let's say we have a competitor that uses an advanced AI system to develop its business strategy. Could you develop a mathematical model to beat this AI in a business environment? And I said, well, I'm sure, I know that people talk about AI, the ethics of AI, and there's people talk about how you can actually upskill yourself in AI, but they say no. You're the person that's come up with the Goldilocks to develop the aircraft carrier. You're the person that does the computer virus for a Formula One car. What we want you to do is come up with a mathematical model to beat an AI in a business environment. So, okay, so I'm thinking in terms of how do we actually model, first, how do we model companies in a business environment? And to do that, first, we have to look at the mathematics of competition, and then we have to go back to a mathematical theorem that was done back in 1657 called the gambler's room problem. And the gambler's room problem goes like this. Let two players each have a finite number of coins, say n for player 1 and n for player 2. Now flip one of the coins from either player, with each player having a probability of winning, and transfer a coin from a loser to the winner. Now repeat the process until one player has all the coins. What is the probability of each player winning, and how long will the game last for? So this was done when Fermat actually challenged Pascal over this game, and this Dutch mathematician Christian Huygens actually developed into a formal theorem. So the question is this, and you can actually try this at home. Let's say if you had two players and you gave them each 3 cards, and let's say you press the random button, or even let's say you flip a coin, and you're saying, if that random number is less than half, B gives 1 card to A, else A gives 1 card to B, and you repeat that process over and over again until one either player A or B have no more cards. And the question is, what is the probability of A losing all the cards? Now, in that case, you've got an even chance that A and B can win a round, and A and B have got the start off with the same initial card. So really and truly, we would expect that the answer would be 0.5. So here we got two players, Fermat, Pascal, resources 3 and 3, probability of winning around 0.5, 0.5. Now by simulation, it's around about 50%, and by analytical equations, it is 50-50. So that's interesting. But let's say if we change it a little bit. Now, instead of having an even number, same number of cards, let's say we have two players, A and B, and we give A just 1 card, and we give B 5 cards, and we press the random generator button. But this time, if the random number is less than 2/3, B gives 1 card to A, else A gives 1 card to B. We go back to step 2. We repeat this over and over again until A or B have no more cards. Now, remember, A has only got 1 card. What do you think the probability of him losing their cards? Well, If we actually do a simulation and also look at the analytical equation of this, the result is quite surprising. The result is actually still almost 50-50. Here we're given Fermat just one card, but we give him a 2/3 chance of winning a resource. Pascal's got 5 cards, but we're only giving him a 1/3 chance of winning a resource. So, but in terms of the probabilities, both by simulation, by equation, even though Fermat has only got 1 card, he has a slight, just over a 50% chance of actually winning altogether and Pascal becoming bankrupt. Now, that is quite interesting. So, but that's the classical gambler's room problem. But how do we actually simulate an actual AI takeover? What can we do? Again, what we're saying that this is big up my maths. What we do is that we take a classical mathematical theorem and we turn it into a new mathematical model. And in this case, what we're doing is, this was my PhD, it's called the extension of the gambler's room problem played over networks. So what we're doing is that instead of playing a game, a gambler versus gambler, what we're doing is we're playing a business versus business in an environment, in a business environment. And what we're going to do is that we're going to introduce new rules that's much more akin to businesses versus a business. So here's a schematic of the extended gambler's room problem. Now what we have is each of these figures here represents a business, and a link means is who they actually are competing against. So what we have is that we'll give each player an initial resource and a target. So they'll start off with an initial resource and saying, right, we want you to go for a certain target. It doesn't necessarily mean all the resources in the network. It may be just I just want to increase my my resources. Yeah, I just want to double my resources. That's my target. And what we do is in each round, we will give each player or a business a random score between 0 and 100. Now, depending on whether your opponent scores higher than you, will determine how many what resource would you actually give to them in that round. Yeah, would you lose a resource to them, or would you gain a resource from them? And then the question is, what we're going to do is now we can actually play the game. So this player is about to achieve their target. So they achieve their target, and what will happen is that when the player achieves its target, they will leave the game, but will have an offspring, which is in business speak a franchise, and they will actually rejoin the network. And so this offspring, the offspring initial resource is the parent's final resources divided by its siblings, and its target will be the same as its parents. And the offspring's strength, which is its highest maximum score, will be the same as its parent. So here, the player is about to become bankrupt. And what happens is that they will leave the game, and you can actually see that this player has actually become isolated, so they will reconnect with another business in the network. And here, another player is about to achieve. You can see that they have offspring that connects to the other opponents in the network. And what happens is, if a player becomes bankrupt, what could happen to the network is that the network could fragment like this. But also, if let's say this player becomes bankrupt, you can see that this could happen. You could have unifications like this, step 1, step 2, like that. Now, the question is, if we actually introduce one AI player, the question is, if we actually implement this one AI player, we have the same rules, but it's slightly stronger. It can score up to 110 as opposed to 100. So in a one-on-one situation with a human business, it stands a 52% chance of winning a resource as opposed to being 50-50 if it was human versus human. So now, if the AI achieves its target, it will have offspring, and its offspring strength will be the same as its AI parent. And so the question is, does the AI takeover emerges? Yeah, does the AI offspring end up dominating the whole of that network? So the question is, now this is quite complex. You've got quite a number of rules there. So what we're going to do is we're going to actually do a simulation. Now let's do a little explanation first. Is in a simulation, what we'll have is that we'll start off with this network of 25 businesses, and the yellow businesses are human businesses. And who they are linked to are who they're actually competing against. Now, the blue is actually the AI business. Now, the number is how young that business. The higher the number, the younger that business. So if you see yellow nose that has the numbers higher than 25, then that's offspring, yeah? And the higher the number, the younger the business is. So the question is, by doing this simulation using the extended Gambles rule problem, do we actually get an AI takeover? So what we're going to do, we're going to load the AI simulation. Okay. So we start off with 2020, and we'll see that the AI population is 4%. 2021. And as you can see, we still get in some new human businesses, 33, 30, 32, 38, but we still have just this one AI business. It's not becoming bankrupt. It's still surviving. (2026), we still got that AI business. It's still surviving. It hasn't become bankrupt. We're having new human businesses here. Now look what happens after 2027. 1 now becomes 3. 3 becomes 4. 4 becomes 6. 6 has now become 8. 8 has now become 9. AI population is approaching 40%. Now, 2034, the AI population has exceeded 50%. Now, at this stage, it's now become a matter of human survival. Now, what we need to now look at is we need to look at the highest number of human business. And at this stage, it's the highest number is 185, because we want to see is the human businesses still creating offspring. Here we go, 190. 198, 199. So the human businesses are still creating offspring, but the AI population is increasing. 215 is our highest number. 215 is still our highest number. We haven't created any new human offspring. And look what happened in 2042. The AI population has now reached 100%. Okay, so that didn't really end it well. But thing is, that was a simulation. The key thing is, what we need to do is that we need to repeat that simulation over and over again. But when we repeated that simulation, let's say 1 million times, what we found is that 80% of the time, it resulted in an AI takeover. But what we wanted to do is that we wanted to look at those 20% of the times when AI didn't take over to understand why, and to see whether we could actually implement those strategies. But there was a problem. The very nature of AI is that it learns, it becomes stronger and becomes stronger. We find that when we rerun this AI against its strategies, when the AI becomes stronger, it would defeat all the strategies aimed against it. So we was not successful in developing a mathematical model to beat an AI. And so one day, I thought, okay, well, really and truly, we're going to go back to the drawing board with this. And so one day, I was watching the news, and it was telling me about this scheme over in America called Obamacare. Now, Obamacare is a scheme that, in terms of what you have, is those patients in America, if they want to go to have medical treatment, they need insurance. And if you're well off, you know, you can afford insurance, but if you're not well off, you can't afford insurance, and so henceforth you don't have the, let's say, the medical treatment. Now, what Obamacare was supposed to, which was done by the government at the US government at the time, was they wanted to say, okay, what we're going to introduce is have a situation where those people who are well off, they will have will increase their insurance premium so that it would subsidize those people who are less well off, and so they can have medical treatment. So that was called Obamacare. Now, opponents of Obamacare said, look, this is wrong. Isn't this just a modern day Robin Hood? You know, all you're doing is taking from the rich to give to the poor. And I was looking at that and I'm thinking, take from the rich to give to the poor. And I'm thinking, well, this is quite interesting. Now, could we come up with almost like an anti-AI AI that after a certain number of time would look at the network and say, how many AI businesses are there? If it's over a certain threshold, we take out we take certain number of their resources and give it to the human businesses. And I was wondering, would that help in terms of minimizing an AI takeover? And I thought, okay, let's have a go. Let's write up this algorithm and say, what shall we call this algorithm? And we should call this algorithm the Obama hood. So what we did is, with this Obama hood, we wrote this algorithm and we decided, okay, what we're going to do is we're going to do the simulation again, but with this time with the Obama hood. And let's do the simulation. Okay, so what we're going to do is that we want to load in the simulation, the AI simulation, and what we're going to do is that we want to introduce the Obama hood. This time, we're going to start off with a much more stronger AI in the middle of the network. And what you'll see is that they actually go to 2 straight away. Still remaining at 2. Increase 2 is now become 4. Back to 37%. Are we going to break through the 50% next year? They seem like the Obama hood is pulling those numbers back. But again, we're moving up to 37%. %. Can the AI break through and create an AI takeover? %. One final push, but it's been pulled back. So in that case, we didn't achieve an AI takeover. So now, doing the plots over time, you can actually see that this is the do nothing strategy, and this is the Obama hood. So in terms of the AI population, it always remains below a threshold. But what is very interesting is that when we repeat the simulation over and over again, what we find is that in the first case, in the first simulation, the AI takeover was at 80%. But in this case, in terms of using the Obama hood, we managed to reduce the AI takeover from 80% down to 3%. In terms of AI extinction, it remained reasonably the same. But in most cases, AI coexistence was at 78%. So that is the Obama hood. So we're moving on to the next stage, is why maths matters part 3. Now, there's a saying that if you go down deep enough into anything, you will find mathematics. This is why mathematics matters. So one day, I was actually invited to take part in a big internet math competition where I was up against a number of invited communicators. There were some communicators from around the country and from America, from Australia, and I was fortunate enough to make it to the final. And what I decided to do for the final was to go on that theme. If you go down deep enough, you will find mathematics. So have a look to see the surprising application of mathematical modeling. Play the video. My name is Dr. Nira Chamberlain, and I'm a professional mathematical modeler. Now, in the mathematical modeling community, there's a saying, if you go down deep enough into anything, you will find mathematics. Have a look at this video called Real World Mathematics. Okay, so final words. Why does maths matters? So Albert Einstein says, mathematics is the poetry of logical ideas. I agree with him. It is a beautiful and powerful subject. And if you go down deep enough into anything, you will find mathematics. This is why maths matters. Thank you.